Whoa. And we're ready. So guys, there you have it. Topics for the day. You'll notice they are 3. Can I ask you a question? Does anybody know the name of that? Yes, it's the and, but there's a name. Do you actually tell me what it is? That's it. I actually, at church on Sunday, had somebody tell me their email address, and they said, it's this and that, and they said, but the and is an ampersand. And I looked at him and I said, you may be the only person on this planet, except for me and now Emmy, that know that that thing is called an ampersand. Did you guys know that? Now you do. It has a name. It's called an ampersand. There you have it. So guys, today what we're going to do is we are going to pick these off one at a time. I'll help you connect this back to what we learned before in just a minute. But understand, guys, this literally becomes a checklist. Each one of these topics stands on its own. So today what we're going to do to wrap up this unit conceptually is we're going to talk about ions. When you understand ions, we're going to talk about isotopes. When you understand isotopes, we're going to talk about average atomic mass. When you understand all of that, you're then ready to get your homework done. Y'all ready to go? All right. So guys, looks familiar, right? What you got? That's the homework we just graded. So guys, why do we grade homework? Because it connects you with what we're currently doing. So because you just graded this, this is familiar. So now guys, let's talk. You may remember that, well, most of you will remember, some of you can't think 5 minutes ago. So guys, when we graded the homework, we didn't grade these 2 columns. How come? Because they are the same as the atomic number. So now let's talk about why. Why is the number of protons the same as the atomic number? Because that's what it's defined as. The atomic number is the number of protons. But now guys, be careful. Why is the number of electrons the same as the number of protons? What does that do to the atom? Be careful, Gracie. What does that do to the atom? Gives it no charge, right? And neutrals out is fine. Protons are positive, electrons are negative. If you've got the same number, they cancel each other out, right? So guys, you got to understand this. The number of protons will always be the atomic number. But you're going to find out today it's not always the same as the number of electrons. So guys, let me set the stage for you here. Here's what we're going to do today. We said ions, isotopes, and average atomic mass, right? So guys, first of all, and you don't need to write this down, this is just the big idea. Guys, we understand that protons are equal to electrons. Or at least they were until now. But again, make sure you're clear. Why are protons equal to electrons? It gives the atom no charge. So guys, the $11,000 question is this. What if the protons and electrons aren't the same? It gives the atom a charge. And guys, we call those charged atoms ions. You don't need to write this down, but the first question we're going to answer is, what if the protons and electrons are not the same? We already answered it. Then the atom will have a charge, and you'll find out in a minute, we call those things ions. Now guys, grab your periodic tables. Grab them, grab them, grab them. Look at helium in the top right corner, element number 2. What is the mass of helium? No, it's not. What's the mass of helium? 4.0, I don't even know it. 4 point what? 0, 0, something, 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 0. Guys, how can that be? And it's critical that you understand this question. Guys, think about this deeply with me. What does the atomic mass tell you? The number of what? Protons and neutrons. Now listen, what is the mass of a proton? 1 AMU. What is the mass of a neutron? 1 AMU. When you add up a bunch of ones, what kind of numbers should you get? Whole numbers. But none of the masses on the periodic table are whole numbers. Anyone want to call me a liar? Where are they, the whole numbers? At the bottom. So guys, check this out. If you look at the top of the periodic table, none of the masses are whole numbers. There are a few exceptions. None of the masses are whole numbers. When you get to the bottom, all of the numbers are, well, not all of them, but a lot of them are whole numbers. So guys, the question that we're going to answer, number 2, is this. Looking at atomic mass, why aren't these numbers whole numbers? And then if you care to talk about it, we can also talk about why are the masses of the ones at the bottom actually whole numbers. Then guys, question number 3 is this. How on stinking earth do we come up with these numbers anyway? How do we figure out the masses of these elements? And guys, what you're going to see is this. The very last slide today is actually extra credit. Let me tee this up for you really quickly. Guys, extra credit in this class is like an oasis in the desert. It doesn't happen much. You're not really going to be sure if it's extra credit because it might just be a mirage. Guys, extra credit in this class, seriously, is a gift. I'm going to give you the opportunity for extra credit for this unit for this quarter in just a minute. And we'll talk about it at the end. It will be due the day of the test, but I'll show you in a minute. And it does not involve baking cookies. I know, very disappointing. So, you guys ready to go? What are the 3 questions we're going to answer? What happens if protons and electrons are the same, aren't the same? Number 2, why are the masses not whole numbers? And number 3, how do they figure out the masses in the first place? And that will lead to the extra credit. You guys ready to go? Yep. All right, here we go. Number 1, what I need you to do is write down the word ions. But guys, we've already defined it. Remember we said question number 1 is what if the protons and electrons aren't the same? What did we say happens if the protons and the electrons aren't the same? The atom's got a charge, so guess what an ion is? It's an atom with a charge. So guys, you don't need to write down what's about to come up on the screen, but I want to use it as sort of a focus point as we talk. So this is the way we started drawing atoms, right? Don't do this, you're okay. But we represented them like this, where the middle is the nucleus and the outer ring is the electrons. And of course, we know this is not drawn to scale, because if the nucleus was the size of a marble, how big would the outer ring be? Lavelle Edwards Stadium. Not drawn to scale, but we can use this to talk. So guys, find carbon on the periodic table. Carbon's going to be our example for the day. Find carbon. What atomic number? What's its mass? What do we now know? Well, because its atomic number is 6, we know that there are 6 protons in the nucleus of a carbon atom. What else do we know then about carbon? We also know that it's got 6 electrons because they balance up until now. Now guys, how many neutrons are in a carbon atom? How do you know it's 6? Good, 12 minus 6 is 6, and that's a carbon atom, right? You guys good? Okay, now let's do this. Guys, let's give this thing a charge. So here's what we're going to do. We're going to turn, and you want to write that down. We're going to turn this thing into an anion. This is 2 syllables. It doesn't rhyme with onion. It's not an anion. It's what is called an anion. So guys, watch what I'm going to do to turn this thing into an anion. Ready? I'm going to come along to this carbon atom. I'm going to give it another electron. I just made an anion. So guys, tell me what an anion is. An atom with what kind of charge? A negative charge. Because now we have more electrons than we do protons. They no longer cancel each other out. We've got an extra negative, which gives the entire atom a negative charge. That is the definition of an anion. An anion is an atom with a negative charge. So guys, what did I do to turn carbon into an anion? Added an electron. So guys, these things are formed by gaining electrons. So we consider them to be electron rich. Anions have more electrons than they should. So guys, how on earth do we give atoms electrons? We bond them to other atoms. That's how bonds form, is by the exchanging of electrons. We'll find out later this is how bonds form, but that's a couple of units from now. So you guys good on anions? You doing good? We're okay? All right. So guys, if we understand anions, I think I can do this. Let me see. Oh, look at that. Okay, so now we're back to normal. We good? Okay, so now guys, what we're going to do is we are going to take this carbon atom and we are now going to turn it, and I'll give you the name first, we're now going to turn it into a cation. This is not a cation, this is a cation. So you ready? Watch really close. What do you suppose a cation's charge is? Positive. So watch what I'm going to do. I'm going to go to this carbon atom and I'm going to take away this and I'm going to give it 7 protons, and now this carbon atom has a positive charge. Do you get it? Go ahead, Garrett. What's wrong with what I just did? It ain't carbon anymore. What did I just turn this carbon atom into? Nitrogen. So guys, that is not the way atoms become cations. You don't add protons, because if you did, it's not the element that you wanted in the first place. So that is not the way we play this game. So guys, what can we do to keep it carbon and give it a positive charge? Exactly. All we got to do is come along here and take away electrons, and now it's got a positive charge, and it's still carbon. You get the idea? Mm-hmm. Good. You always work with the electrons. So guys, this then is a positively charged ion. It is formed by removing electrons, and therefore these things are electron deficient. Guess what this does to atoms? Makes them really reactive because they want their electrons back. We'll talk more later. Okay, so guys, this is a good time to call time out. We now understand that the positives and negatives don't have to be the same. If they're not the same, the atom has a charge. That charge could be negative, which we call an anion if we add electrons, or that charge could be positive, which we call a cation, if we take away electrons. Questions, things you want to explore with this? Or are you feeling good about ions? Remember, we're checklisting. We good on ions? You sure? I'm fine if you're fine. Okay. So guys, if you're good with ions, draw this into your notes. Let's check and see. It only needs to be big enough for you to write in it. But guys, put together a calcium +2 ion. Actually, you know what? I'm going to do this the right way. Don't write down +2. It should actually be calcium 2+. We may as well do it right. Okay, so here we go. So guys, put together a calcium 2+ ion. That means it's got a +2 charge. Isn't that the hardest part of this right now, is finding the elements? Guys, it's on the right-hand side, second column, 3 or 4 lines down. Yes, I do know where most of the elements are. You guys realize in the next unit, I'm going to have you memorize the names and abbreviations and masses for all the atoms? No, I'm not. See, now all of a sudden I'm your hero. So why would I have you memorize something that you can just look up on a periodic table? I like that it doesn't take much to impress you guys. That's a good point. You're right. Just sparing you work is like a gift from heaven. All right, guys. So as we pull this together, now that you've found calcium, what I would suggest you do, at least at first, and it's up to you, but certainly you want to do the nucleus first, because as David pointed out, the thing you're messing around with is the electrons. So you may as well establish your nucleus first. So Guys, for this to be calcium, it's got to have 20 protons. How do I know? Because calcium is element 20. Every atom of calcium has 20 protons. If it doesn't, it's not calcium. So now we need to know the number of neutrons. The mass of calcium rounds to 40. 40 minus 20 is 20. Now, guys, common mistake. If, and I'll just tell you right now, this is an essential. If you can't do this on the test, you'll be coming in for remediation. So guys, this is an essential. So let me tell you one of the common mistakes on this. So how many electrons should calcium have? 20, right? So if you do this wrong, this is a common mistake. You go 20 electrons plus 2 is 22, because this is a plus 2. Right, and guys, remember the reasoning is inverted because electrons are negative. So if you want a plus 2 charge, you want 2 more positives than negatives, and so it's counterintuitive because you're actually subtracting. So when you see plus 2, you're taking 2 away. So now, guys, let's take that similar logic and let's look at nitrogen with a -3 charge. Nitrogen is element number 7. It's a neighbor of oxygen. You'll find it. You guys know this, right? 70% of the air that you breathe is nitrogen. It's absolutely worthless to us. It goes in and comes right back out. We're going to talk more about that in early December. But you're right, John, that those are actually all the charges that nitrogen can take on. We're just looking at -3. Did you guys see what John's seeing? Right above the abbreviation of nitrogen, you'll notice a lot of small numbers. All of those small numbers are actually all of the charges that nitrogen can take on. We're just looking at -3. It'll show you. Okay, guys, so here we go. Nitrogen is element number 7. It has a mass of 14, so it is also 7 neutrons, 14 minus 7. Now, guys, how many electrons does nitrogen want? 7. But if we want to give it a -3 charge, be careful. What do? Add 3, and how many do we then end up with? 10. Okay. So, guys, this is the time to call timeout. Ions, atoms with a charge, you need to know their names, you need to know how they're formed, and you need to be able to figure out what they're made of. Anything there you want to talk about? You guys good? Can we check it off the list? Go ahead. Yeah, so it's interesting. One of the ways to do it, well, we talked about forming bonds. That when atoms bond together, many times they're gaining and losing electrons, and as they do, they become ions. And then, interestingly, those ions attract and they form compounds. But we can also take ions, and you're going to find this out in the, this is why I'm talking about it, because you need to know this for the extra credit. The other thing that we can do to turn atoms into ions is blast the atoms with radiation. It's actually got a name. It's called ionizing radiation. And if you can take an atom and hit it with radiation, depending on the radiation you're hitting it with, you can either get that atom to absorb electrons and become negative, or expel electrons and become positive, which is a step along the way to the process that you might want to look at for the extra credit. So, you guys good? Okay, here we go, number 2. We've got ions checked off the list. Now it's time to talk about isotopes. Man, someone keeps stealing my pencils. All right, so guys, you ready? It's time to have the isotope talk. And it goes like this. Guys, it does not matter if I've got a old school pencil or if I've got a mechanical pencil. Both of these pencils have got the same thing in the middle. And it's not lead. It's graphite. And guys, it's actually kind of embarrassing. It sort of tells you the world that we live in. Because if you grab if you grab one of these, which is where you get your graphite, it actually still says black lead on it. If this were lead, there would be lawsuits spinning all around whoever this company is. Because, guys, lead is a neurotoxin. We can't have lead in our homes. We can't have lead in our paint. We can't have lead in our gas because it's deadly. This is not lead. It's graphite. Now, here's the question. What's graphite made of? It's actually pure carbon. So, guys, when you look at this stuff that is inside your pencil, it's not lead. It is graphite. But graphite is actually pure carbon. It looks like this. If you could look down inside of the graphite that is inside your pencil, what you would actually see is this. You would see sheets of carbon atoms in 6-member rings that are actually laid out in sheets. Those sheets are called graphene sheets. And these sheets are actually related to other sheets of graphene by these weaker interactions that are represented by these purple sticks. That, guys, is why if you take your pencil and tap it on the tabletop and it shatters, the reason is because these sheets can flex. And when they flex, they will actually break, and that's why this stuff shatters so easily, because it's actually not tied together very well. Now, guys, the thing that's interesting is this. If you could take this and get all of these atoms to bond together like this, guess what it turns into? Diamond. The only difference between the graphite in your pencil and the diamond in your ring is that in the graphite, these things are in sheets, and in diamonds, they're all interrelated. There's actually a company down in Springville that takes graphite and turns it into synthetic diamonds that they use in oil rig drill bits. But anyway, so guys, this is what is inside your pencil. So now we're going to focus on these carbon atoms, because guys, this is the thing that's weird about this. All of these atoms are carbon atoms. So what we're doing is we're zooming in into what's inside your pencil. And guys, all of these atoms are carbon atoms. So what do they all have in common? They're all carbon atoms, but what makes an atom a carbon atom? Look on the periodic table, guys. If you don't understand this, you're not keeping up. What makes an atom a carbon atom? 6 protons. What if I add a proton? Now it's nitrogen. So guys, what do all of these atoms have in common? They all have 6 protons. But here's the thing you now need to understand. They all don't weigh the same. Guys, there are some atoms of carbon inside your pencil that weigh more than the others. There are atoms of carbon inside your pencil that weigh less than the others. They all are carbon, but they have different masses. And guys, this is what we call isotopes. So guys, isotopes are atoms of an element that have different masses. So guys, here's the question. How can that be? How can you have atoms of an element that don't weigh the same? Because we've already established they all have the same number of protons, right? So how can we have atoms of an element that don't weigh the same? What must be going on? Let me show you. Guys, it goes like this. Don't write this down. So if we could take the carbon that is inside of our pencil, and if we could grab, and think about this, guys, if we could take the atoms of carbon that are inside our pencil, and how big are those atoms? What if we took those atoms of carbon and blew them up to the size of a blueberry? They'd be the size of the earth, right? If there was a grapefruit. They're ridiculously small. So guys, if we could take these atoms, and if we could weigh these atoms, how do you weigh individual atoms? That's actually the extra credit question. Guys, if we could take these atoms and if we could weigh them, this is what we would find out. We would find out that there's actually 3 different carbon atoms inside a sample of carbon. They're all carbon. They all have 6 protons. But guys, some of them are a little bit lighter than the others. Some of them actually have a mass of 11. And then guys, there's some other carbon atoms that actually have a mass of 12. And then there are some other carbon atoms that have a mass of 14. Maybe you've heard of carbon-14 radioactive dating. It's the way we figured out how old the Dead Sea Scrolls and things like that are. So guys, this is actually what is inside any sample of carbon. Some of the carbon weighs 11, some weighs 12, some weighs 14. But guys, if they all have 6 protons, how can they have different masses? Go ahead. Exactly. Guys, it's a different number of neutrons. So how many neutrons does carbon-11 have to have? 5, because 6 plus 5 is 11. How many neutrons does carbon-12 have? 6. And how many neutrons does carbon-14 have? 8. So guys, which one of those is really carbon? They're all carbon. Guys, carbon-11, carbon-12, and carbon-14 are all carbon atoms. They react the same, they look the same, they do the same chemistry. They are all carbon. The only difference is their mass. And guys, we call these isotopes. So think about this. What is an isotope? They are atoms of an element that have different masses. They're all the element. The only difference is their number of neutrons. Does that make sense? So guys, let me bring this back to you then, because this is what we're then saying. So isotopes are atoms of the same element that simply have different numbers of neutrons. Now guys, you got to understand this. There is no correct isotope of an element. It's not like carbon-12 is really carbon and carbon-11 and carbon-14 are mutants. They're all carbon. So guys, you ready to answer the second big question of the day? Why are these numbers on the periodic table not whole numbers? Why are they not whole numbers? They're the average of all the different masses. Does that now make sense? Because guys, when you take a sample of carbon, some is 11, some is 12, and some is 14. And when you figure out the average mass of all of those numbers, you find out the average is 12.011 or whatever it is on the periodic table. But guys, here's an interesting question. If we've got 11 and 12 and 14, why can't we just add those up? Why is that mass not really the average of 11, 12, and 14? The answer, guys, is because it's not 1/3 carbon-11, 1/3 carbon-12, and 1/3 carbon-14. Which one do you suppose there's more of? Carbon-12, which is why the average is closer to that than it is the average of just the 3 numbers. You get it? Go ahead. What? Could there be 15 different isotopes? Oh, could there be a carbon-15? Is that what you're saying? There could be, but there isn't. So the problem is that some of these isotopes are so unstable that they immediately fall apart and they don't exist for long periods of time. So not all possible isotopes are possible. Okay? So guys, this then is why there's no correct isotope. All the atoms of an element are isotopes of each other, and they all behave chemically exactly the same. So guys, the question then becomes this. How do they figure out the mass of carbon? How do they come up with that number 12.011? It's not the average of 11 and 12 and 14 because there are different amounts of the different elements. So how do they arrive at that number? Well, guys, I'm going to show you the math in a second, but I'm going to show you not using carbon as an example, but using another element as an example. But that's the last thing we need to talk about. So guys, are we okay with this concept of isotopes? They're atoms of an element with different numbers of neutrons and therefore different masses, understanding that there isn't a correct isotope, that these are all isotopes of each other. It just means they have different masses. You guys good? All right. So guys, let me show you another example. Please don't write this down. But guys, David asked an interesting question. He said, can there be carbon-15? Can there be carbon-16? And the answer is no. Not all isotopes are possible. I bring that up because this could cause confusion. Guys, I want to show you another set of isotopes. And the problem now is you're thinking, wait, carbon had 3 isotopes. Now we know that neon has 3 isotopes. Does that mean all elements have 3 isotopes? And the answer is no. Some don't have any. Some only have 1. Some have 4 or 5. I'm just happening to show you 3. So guys, neon, the stuff that is in a neon light. Guys, neon actually exists as 3 different isotopes. Notice they're all neon, so they all have 10 protons. So guys, find neon on your periodic tables. It's on the right, it's in red, it's 1 box down. We know that neon is element number 10. I don't remember. What's its mass? What is it? 20.17, so it rounds to 20. It's a little bit higher, is that right? A little higher than 20? So guys, the idea is this then. We know that the mass of this is not the average of 20, 21, and 22, because the true average of these would just be 21. So how do they figure out that number, 20.1 whatever, given these masses? Well, here's what we know. Neon exists as what we call neon 20. It's got 10 neutrons. Neon 21, it's got 11. And neon 22, it's got 12. So guys, the question then becomes, how do we figure out these masses? This is the last thing we're going to talk about today, and it goes like, well, actually, it goes like this. We'll fill this out, and then we'll talk about it. So guys, you know what? Maybe I should slow down. I'm realizing we haven't done isotopes quite well enough. Let me go back here and make sure that we're okay with this. We should do this. I was going to skip it. I wanted to just transition right into the next thought. I'm realizing it's a bad idea. We should do this first. So guys, do this with me. We've already done this one, but let's do it together to make sure you understand how this goes. Yeah, I totally forgot I should do this with you. So let's do it. So guys, we're going to piece together a carbon-14 atom. It would be a mistake to skip this. This is why this would be a mistake to skip this. Because it goes like this. Carbon is element number 6. So it's got to be 6 protons. Now, how many electrons does it have? Also 6. It doesn't have a charge. If it did have a charge, it would look something like this. But it doesn't have a charge, so we just assume it's neutral, and we call it 6. Now, guys, how many neutrons does carbon have? Well, if we looked at the periodic table, we would see that carbon's mass is 12. 12 minus 6 is 6. But guys, the trick is this. This number right here, 14, is telling us don't look at the average mass, use that mass. So guys, how many neutrons does carbon-14 have? 8, good. So here's the rule. If they give you the mass, use it. If they don't, use the average that's on the periodic table. So guys, let me show you another example. Oxygen 17. Figure it out. What is in oxygen 17? Okay, so guys, did y'all find oxygen element number 8? When you find oxygen, you find out that it's element number 8, which immediately tells you protons and electrons because it doesn't have a charge. But now, guys, realize we don't need the periodic table to find the mass because it's telling us 17. So when the mass is given, whether it's like this or like this, when the mass is given, we use it. So we know this has got a mass of 17, so how many neutrons have got to be there? You got it, 9 neutrons. Please. Yeah, Jerry. Yes. Yes. Yeah, so, hey guys, Jared's question's good. I'm going to paraphrase if you don't mind. I think what Jared's asking is, can something be an isotope and an ion, right? And so, and forgive me, but don't all ions have to be isotopes? Because any particular atom has got a number of neutrons. It's not necessarily the average. So, because all atoms are isotopes of each other, it would be completely fine to say, look at this particular isotope with a charge. So absolutely, we can do both together. Does that make sense? You guys good? Okay, go ahead.
Does the periodic table list all the variations of isotopes per atom?
The periodic table doesn't. You can look them up. You can just Google isotopes of carbon. And it lays it out there. Actually, what you should probably Google is stable isotopes of carbon so that you know which ones actually persist. But yeah, you can look. It's not on our periodic table, but you can look them up. Yes, sir? That's a beautiful question. So why do these isotopes exist in the first place? And so the answer is this. You know, we found out that elements are formed in stars, especially things like carbon and oxygen, the heavier ones in supernova. But when they form, they don't all form with the same number of neutrons. Some have more, some have less. And so what happens is all of these atoms are actually just funneling down towards stability. So what is it that makes these atoms stable? And the answer is, at least for the lighter atoms, the answer is equal numbers of protons and neutrons. Actually, if we have time at the end of class, I'll Google the graph and you can see it. They graph the number of protons minus the number of, protons and neutrons. And what you'll see is that we call it the line of stability. And for the lighter elements, it's a 45-degree angle. So equal numbers of protons and neutrons tend to be stable for the lighter elements. As we get into the heavier elements, they need more and more neutrons in order to be stable. So the line is almost parabolic. So as these things get heavier, they need more neutrons to be stable. But that's why these isotopes exist, is these atoms are falling apart. We call it radioactivity, working towards stability. And that's what we're going to talk about in the next unit, is that idea of stable ratios and where they're trying to get. And that determines the type of radiation they release. So yeah, that's the whole idea behind this. You guys good on isotopes? Good on ions? Good on isotopes? Can I show you the first page of the test that you're going to sit down to next Wednesday? Because guys, it looks like this. This is it. This is what the first page of the test is going to look like. Guys, I'm not going to give you time to write it down. What I would like to do is do this with you. If you would like to reference this as you're studying for the test, watch the screencast. But guys, this is what you're going to be doing on the test on to the first page. But guys, these are also essentials. If you can't do this stuff, you're going to be in remediation. This is critical. It's not the only essentials, but this is critical. So guys, we're going to do these together. Just play along with me. I think you can mentally think about what you would be doing. So guys, looking at the first one, this is magnesium. So we're going to write down the abbreviation magnesium. Now this is Mg, so find magnesium on your periodic table. It's on the right. Yep, element number 12. It's a couple lines down. So guys, magnesium is element number 12. What is its mass? 24. So guys, now we know all that we need to know to put this atom together. So how many protons? 12. How many neutrons? 24 minus 12, 12. How many electrons should magnesium have? 12. But it's a +2 charge, so we don't add 2 to make it 14. We remove 2, and this would be 10. Guys, please ask questions as we go. You okay? Now look at the next one. Guys, this is lead. Find it. It's element 82. So guys, lead is element 82. What's its mass? Doesn't matter. Guys, watch carefully. I led you into that. So lead is element 82. It's abbreviated PB. But lead is element 82. What is its mass on the periodic table? Doesn't matter. The reason is because they tell us right here that we don't care about the average mass. We're going to use 209. So anytime they give you the mass, don't even look it up. Use the one that's given. Now we go from here. Go ahead. Yes, and actually I was going to do that at the end, but let's do it now. The other thing that you've got to do is put the 209 right there. Anytime we're looking at an isotope other than the average case, and you're exactly right, it's not just in the name, it's also in the abbreviation. Yep, okay. So now guys, protons, 82. Electrons is also 82. And then neutrons would be 127. Can I subtract? Is that right? Is that right? Okay. So guys, the number of neutrons would be 127. You okay? So guys, let's do these last two. This third one is a bugger. This is like graduate level fill in the boxes. So guys, this is aluminum. You're asking yourself, how hard can this be? It's aluminum. Yep. So guys, good. So the first thing, guys, is this is aluminum 25. Well, you know what, Marcos? Maybe we should talk people into that because I'm not sure if they followed it. So guys, let's now find aluminum on the periodic table. What element is it? 13. Now, what is the mass on the periodic table for aluminum? 27. But guys, watch. The average mass is 27, but this says 25. So that's telling you, don't use 27, use 25. So now where does that 25 go? It goes here, and as Cation pointed out, it goes there. Now we can fill in the table. 13 protons. How many neutrons? 12. 25 minus 13 is 12. Now guys, check this out. Aluminum should have 13 electrons, but what is it telling you? 10, which means it's positively charged, positive 3. So now we need to put the charge right there. Does it also go on the aluminum in the name? It does not, but the charge goes there. So guys, this is as crazy as this gets. If you can pull through that, I think you're going to be okay. You okay? Questions? I'm so glad we did that. I was going to skip that, and that would have been a huge mistake. You guys good? All right, guys, let's wrap this up. Last question. Going back here. So guys, what we're going to do now, and you want to get this in your notes, this is our third point. And you know what? All you need to write down is this. Don't write down this stuff, just write down this. Calculating average atomic mass. And don't write down anything else until I tell you. So guys, this is the idea. We're now going to figure out how they come up with these masses. So here's what we know. There are lots of different isotopes of most of the atoms that exist in nature. So how do they then figure out these average masses that make it onto the periodic table? Well, guys, in order to do this, what we need to do is we need to know two things. We need to know the mass of each one of the isotopes. So if we take a piece of graphite, we need to know that some of this weighs 11, some of it weighs 12, and some of it weighs 14. We need to know the masses. But the other thing that we need to know is how much of each of those exists. It's not a third each. So we need to know how much weighs 11, how much weighs 12, and how much weighs 14. We call that abundance. So guys, come back to this. Remember our neon sample? How many different isotopes of neon exist? 3. What are they? They're neon 20, neon 21, and neon 22. So guys, what we just figured out is the mass of each one of these isotopes. What else do we need to know? How much of these exist? And guys, this is interesting. In the neon, in a neon sign, it actually sorts itself out this way. Neon 20, 21, and 22. But guys, in a sample of neon, 90.5% of it is neon 20. And then 0.270% of it is neon 21, and then the remaining 9.3% is neon 22. Guys, this is the data that we need to figure out the mass of neon that's on the periodic table. So how do we do it? The answer is this, and this is what you want to write down with me. Guys, this is the equation that allows us to figure out the mass. Again, you remember that you don't have to memorize equations in this class. It will be given to you. You just need to know how to use it. Oh yeah, we'll talk. Just write it down. So guys, here's what this equation says. It says AAM, which is average atomic mass, is equal to squiggly E times the quantity, mass times percentage, plus 100, or divided by 100. So guys, let's talk about squiggly E. Guys, squiggly E is actually a capital Greek letter. It is the Greek letter sigma. We later took the Greek letter sigma and turned it into what letter? S. This is actually S. Epsilon became E. So guys, this is actually the letter that we adopted is S. So if we take that backwards, sigma actually represents our letter S. And that S is actually the abbreviation for the mathematical term sum. And what does sum mean? To add things together. So guys, this Greek letter sigma is actually the abbreviation for the word sum, which means to add up. So what this is telling you is you are going to take the masses times the abundances, and you are going to sigma them. You are going to sum them. You are going to add them up, and that will give you the average atomic mass. So guys, look at what we need. We need to know the masses. Well, they're right here. And we need to know the abundances. They're right here. And guys, that is all the data that we need to do the math. So what does it look like? It looks like this. Do it with me. Average atomic mass is equal to. And we are going to take the first mass times abundance. So what is the mass? 20 AMUs. What is the abundance? 90.5%. And we're going to multiply those. Don't forget units. Then what are we going to do next? Well, we are going to sigma. We are going to sum. We're going to add them together. And what are we going to add to that? Well, we're going to take the next mass times the next abundance. So 21 AMUs times 0.270, and we're going to sigma that. We're going to add it. And then we're going to do our last sigma. We're going to take this mass, 22, times its abundance, 9.30%. We're going to sigma that, add it all together, and then divide by 100. Now, guys, let's talk. Before you do the math, and I want you to do the math because you're going to get really frustrated with your TI calculators when you do this. Guys, let's talk significant digits first. This is important. Guys, these numbers right here, these are the masses of these things. But what do they really represent? The number of protons and neutrons. And guys, because you can't have fractions of a proton or neutron, these numbers are understood to be perfect and therefore do not limit significant digits. So your significant digits will only be limited by your percentages because those are measurements that could be inaccurate. So we've got 3 significant digits, 3 significant digits, 3 significant digits. So you get 3 in your answer. The bottom line is, guys, don't look at the masses when you figure out significant digits. So you'll get 3 in your answer, and when you've done the math properly, you'll come up with the answer 20.2. So guys, I'm going to pause for a second and give you a minute to try to do the math. Go for it. When you find yourself getting really frustrated with your TI calculators because they are so ridiculously nitpicky about orders of operations, use parentheses. That's the answer. So guys, you'll know that you have chugged this through your calculator properly when you get the answer 20.2. Interestingly, you will find that that's the same as the mass of neon on the periodic table, rounded to 3 significant digits. Yeah?
So for the percentage, are we going to turn that back into a decimal?
No, so that's the trick. So we're going to leave this as percentages, and that's what the dividing by 100 does. Okay. You'll see in other chemistry texts that what they actually do is they divide each of the percentages by 100 first. So they would turn that into 0.905. Okay. But if you do that, then don't divide by 100 again. Because that's all that's doing is converting the percent to a decimal. So guys, again, if you have made peace with your calculator, you should get 20.0. But when you're doing this on the homework and the test, and if you're not sure if your answer's right, guys, where does your answer have to be? Between the little number and the big number. Averages have to be in the middle, so it's got to be higher than 20 and less than 22. You guys all okay? Jake, you're kind of having a squirrely day today, aren't you? You having a hard time sitting still? A little bit. You guys good? Okay, so guys, if you're not getting 20.2, I don't want to slow everybody down to help you with your calculator. Grab somebody around you that knows how to run a TI calculator and let them help you. Go ahead, Jared. They're given, these numbers are all given to you. Yeah, no. So you'll always be given the mass and the abundance, the mass and the abundance, the mass and the abundance. You just do the math. You're good? But guys, here's the thing that's interesting. Jared's question is exactly what we're going to talk about in extra credit. This data will be given to you. But guys, this data's got to come from somewhere, right? How do they know that this is 90%, a 0.25%, and 9.3% these isotopes? Well, guys, the answer is literally this. They take a sample of neon and they separate the atoms into piles. They go, here's all the neon 20, here's all the neon 21, here's all the neon 22, and then they count each of the atoms. They say, here's how many atoms are in this pile, how many atoms in this pile, how many atoms in this pile, and they count and weigh atoms. How on stinking earth do you count and weigh things that we can't even see? Remember, blueberries in the earth. Guys, how do we count and weigh things that we've never actually seen? That's the extra credit. And it goes like this. Guys, this is your extra credit challenge. The answer to the question, how do we count and weigh atoms, is what is called mass spectometry. So mass spectometry is the process used to determine the relative mass and abundance of isotopes in a sample of an element. For this extra credit assignment, you will explain visually and verbally how mass spec works. You're welcome to use whatever resources you want, but be sure to cite them. So guys, here are the requirements. It's going to be 1 page, not more, not less. On the front of the paper, you're going to write a 12-point double-spaced explanation of how mass spec works. And it's going to be very apparent if you are simply plagiarizing or if you are reading, understanding, and explaining. If you're plagiarizing, you're not going to get credit. You should get kicked out of school. But if you can explain it, I'd love to give you credit for it. So guys, at the bottom of the page, you're going to cite your sources. So this is something that is your explanation. So imagine that your audience is a 7-year-old. And some 7-year-old comes to you and goes, hey, Uncle whoever, how do they count and sort atoms and then weigh them? That's your audience, okay? Then guys, the back of the page will be a hand-drawn, not a JPEG off the internet that you print. It will be a hand-drawn representation of a sample passing through a mass spectrometer. You're going to label the parts and make sure that you show the resulting separation of isotopes in the detector. And that doesn't mean anything to you right now, but it will when you do the project. So guys, I don't expect you to write all of this down. I will post this on the internet right now under today's date. And so if you're interested in extra credit, the extra credit will go in the homework section of your grade. Here's the problem. Most of you have already perfect scores in homework, and Skyward will not allow you to go over 100% in any category. So guys, if you do the extra credit, and if that pushes you over 100% in the homework category, I will hand calculate your grade and do a grade override at the end of the quarter. Okay? So this isn't just going to top up your homework score, we'll allow it to go over the 100% threshold. The only problem is you won't know what it does to your grade until after the end of the quarter because I have to hand calculate your grade. So guys, I will post this online so you don't have to write it all down. These are due the day of the test. So they're not due on Monday, they're due on Wednesday. No, I will not accept them late. It's extra credit. So either you turn it in the day of the test or you just chose not to do it, okay? So that's that. Guys, in front of you, you've got your homework. Let's grab them. Page 3. And guys, this is the test. Wow, I didn't even, here, let me. So guys, ready? First page of the test. Last page of the test. First page of the test, last page of the test. On the test, you will be filling out one of these tables. Last page of the test, you will be calculating average atomic mass. What's in between? All the other material. Wouldn't it be nice to know what all that other material is? I've already told you. Guys, the study guide is posted on our website. We will not be putting study guides in your homework packets anymore, but it's posted on our website. So guys, as you're studying for this test, let me show you. Go out here to our website. The day of the test, which is in October, is right here. And guys, this is the study guide. You'll notice that it's broken into the things you need to know and the things you've got to be able to do. You know how to study for knows and do's because I taught you. So guys, there's the study guide. Printed as you study. Guys, we will not give you the study guides anymore. But I've already told you the first and last page of the test. So guys, the remainder of the chart is yours. You've got 15 minutes. I may get homework done. Don't forget it is pages. I'll stick the answers up on the wall, and then I will post the extra credit assignment. Go get